Hello, everyone. My name is Emna Amri. I'm heading the Innovation Department of CYSAT. So on behalf of CYSAT, the organizer of CYSAT, I would like to welcome you all in this session. I hope you had a nice lunch break. And now we will start with the next track today, which is about quantum resilience. So just like to start, we will have 3 talks about quantum resilience of space infrastructure here in the central room, which are quite technical. Then at 3:30 on the master stage, for people who are interested in the topic, we will also have a panel about quantum resilience with a more broader overview involving all type of perspective, not only technical, so it will be also everything related to policymakers, geopolitics, and everything. So please don't hesitate to go to the master stage if you are interested. Now, let's start with our first speaker for this session, and let me introduce Mr. Juan Bousquet, senior researcher at the Stratosphere IPS lab. Juani has spent the past 15 years at the intersection of technology, security, and innovation, with a master's degree in cyber defense and cybersecurity, and a thesis on satellite security developed at the Stratosphere IPS lab, Czech Technical University in Prague. He has built a career focused on securing space systems. So welcome, Juani, to the stage.
Well, thank you so much, Emna, for the presentation. And thank you, everyone, for coming to this talk. It's an honor to be here on this conference and also to have so much people here. So thank you. Okay. Today, we are going to see this talk that is about a research. It's like a pure research that I did in the context of my master thesis. I'm Juani, I'm from Buenos Aires, Argentina. I'm currently living in Spain, and actually I started my master thesis in Argentina and then finished my master thesis in the Stratosphere lab. And it was pretty cool because at the time I was working at Satellogic, which is a company that runs satellite constellation in the cybersecurity team. And I was wondering what more we can do in order to protect satellite, protect images, and protect links, and protect all these things. So for today, this is more or less the agenda, the roadmap. And to start, this is more or less what Emna said. This is my little roadmap in this cybersecurity world. I did my master thesis, as I already mentioned, in Argentina, then the thesis in the Stratosphere lab, and also all the code, scripts, and experiments that we are going to see now, and the thesis is full open source, so you can check it. And the cool idea about this is how to open everything and to start talking with professionals and to start getting more researchers that put focus on space cybersecurity. And okay, first of all, when I was thinking about this master thesis and how this is going to work regarding satellites, first is why integrity matters. And when I was in the company in Satellogic, and something that happened is like, if you have satellites, for sure you have attackers that have a lot of money. For sure you have people that has pretty good intentions and reasons to try to get information from you and to try to get your assets in some way. So when I started the thesis, I tried to focus how we can see actors and threat actors that has a lot of power, let's say that way, and they for sure have access to 0 days, to have access to a lot of things that we can even detect. So I tried to go to the lowest level. I tried to think in integrity. So for sure, if there is any change, if there is something that is going to happen in the satellite, for sure it's going to be a change. So I try to focus on integrity. And in this specific talk, we're going to focus on the experiment. One of the experiments of the thesis was how to protect an image that was taken by the satellite in all the travel from the satellite to the ground station. So why the integrity matters in this case that we're going to see today? And the thing is like how we can protect an image. If an image is a file, if there is any change, we're going to see a change, for example, in a hash. So why it's important, for example, to protect an image that is taken from the satellite. And something that is really important today, for example, in defense and intel clients, it's that it's important to protect the image because we can have threat actors that have access to the ground station and in some way can get this image, and of course they can do something with it. And what happens if that image just arrives to your hands and you don't even know that it was changed in some way? So, and what happens also if you have also files, not only images? We are going to focus on images, but the thing is like you can have files and data. So I try to focus also in TPMs, the Trusted Platform Modules, and these tiny silicon chips. Maybe some of you already know what it is. How many of you know or ever listen about a TPM? Put your hands up. Oh my God, that's good. Well, the thing is like I have an issue, and it's when I'm trying to start my research, I couldn't find papers or something published. So that was a pity. And this research started 3 years ago. So now we have some information. Also, we start talking with some colleagues, and they tell me like, hey, now we have some information about that. So for those that, more or less, we are going to do a quick summary. So what we get with the TPMs is that we have this hardware root of trust. We can try to store the private keys in a secure place. And also, it's supposed that they cannot be extracted. And also, something that is important is that we are going, or we can tie that TPM with that signature to a specific satellite. And something that I really wanted to do with this experiment and with this use case is what happens if I have a TPM, and what happens if I can tie that identity that is the TPM for me to that specific satellite. What happens if I, for example, can say in some way that if the satellite take a photo, and then that photo is going to go past and through all this workflow, where I just take the photos, then that photo is signed, and then that comes to the ground station, it's verified, and I can guarantee that that image came from that specific satellite. So this case is pretty interesting. Currently, at the time of this research, I use like ICC that came with the TPM in order to sign. But the thing is like, of course, that changed because now we have quantum and we need to do something about it. And we're going to see it in the next slides. So something that that I already mentioned is like, for me, the most important property that we have tying with this identity of the TPM to the satellite is we have traceability. So that's one of the most important key things that I really want you to have in mind when you leave this room. In order to try to test all of this, because I was a student, I don't have so much money. I take like 2 Raspberry Pis, and I just design and say, okay, if I have 2 domains, because I started thinking about if I isolate a domain where I have the camera of the satellite and where I just sign the images, separate with the main domain. So what you are seeing now is like these 2 Raspberry Pis. One have the camera. That's like the place where in the satellite, let's say that way, the image is captured, then it's signed, and then in another Raspberry Pi is like the main board of the satellite. And then I use a pretty cool solution that is like the Let's Trust TPM. It's a guy that, as a master thesis, just put an Infineon TPM inside an USB support, so you can use it pretty easily. So I just simulate some attacks in the main board, and also I try to simulate how it will be like take the photos, sign, and try to send it through the main board, and then trying to send it to the ground station. So more or less, this was the workflow I just get. Something that has the TPMs is the lockout counter, which is something pretty cool. It's one of the many layers of security that it has, that it prevents of using the TPM for unauthorized access. And in case it's happened, it just triggered a counter, and you can check it before doing the signature process. So you can check with the TPM, hey, have you been used unauthorizedly? Yes, okay. Then I check the counter and say, okay, we need to check another things more before progression. So on the thesis, I just thinking about what about the hashing process and what hashing algorithms and can I use. So have in mind these Raspberry Pi boards have 10 years old. So the idea was to use like pretty old hardware in order to do all of this project. So I tested different algorithms. I just get the SHA-3 256 that today is one of the algorithms that is still safe in quantum era. And also, I still do the signing process using the ACC ACDCA. And well, it's a process of signature. It creates a package, and then it's ready to be sent. But what happened with the quantum threat? What happens today with quantum era? So something that is important to mention is that we have the CNSA. This is the Commercial National Security Algorithm Suite. This is published by the NSA and NIST. And this timeline, which is for sure an American one, just mention what are the deadlines or the dates that we need to have in mind in order to do all this transition to quantum algorithms and signatures and so on. So why this is important? Because of everything that we already know. Attackers could just harvest now and decrypt later attacks, and for sure RSA, ACC, DSA are already broken. So we need to have this in mind, because the satellites are going to be up in the space for sure for 5 years and more. And it's important to start doing this transition before the end of 2030. So that's more or less this part. But the thing that's important to mention is like, this is like the American, what American says, like we have this kind of algorithms that we can use. We're going to see what's the process to use MLDSA, but also there is a key tension between Europe and United States and the rest of the world, because for sure we have different kind of algorithms that could be used, and for sure this is an ongoing discussion that is happening now. So something that is important to say too is like, can my TPM do PQC? And the answer is, as far as we know, the commercial TPMs, no. But the thing is like, for sure, if we start talking, there is some process of TPMs that start using post-quantum algorithms. But as far as I could research at the time, and also that are available today, I know there are some companies that are working on, but it's not public available. So the thing is, what can we do if we can have our TPMs that protect the private keys and has these interesting properties of tie and identity to a satellite? So we have the guys of our wolfSSL, that the thing is like, they have a solution, but it has the things that needs to be improved. And in this demo and with proof of concept that we're going to see, they just publish the possibility to use MLDSA This is something that is quite new, because if you just check GitHub, they've been like working a lot at the end of 2025. But the thing is like the final merge of this solution that is full working, let's say that way, happened like 2 weeks ago. So we could say that we have this post-quantum possibility and algorithms to be used, but only by software. And this is something from 2 weeks ago. So what I tried to do, and this is something that happens for CYSAT, it was like, okay, we have this thesis, we have everything, we have the TPM, so how we can have this transition to quantum era. So what I just tried to do is like, okay, let's say we have the image that is captured by the satellite, then we use SHA-3 256 as an algorithm to do the hashing, and we could say that, okay, we are trusting to this algorithm, because if it's broken, we will have more problems than the satellite. But the thing is, like, I use the same hashing algorithm, and then what I did is like sign that hash that I produced from that image. So I took the classical path, so I still have the TPM doing the ACC, ACDCA signature, because I really still want that identity tied to that satellite in this transition, in this hybrid approach. And then I also add this this new branch using the MLDSA tree from Wolf, and then I just create this hybrid signet package where I have different components. So what we're going to see now is this proof of concept of hybrid signing, and basically what we have here is okay. I create like the directories where we're going to work, and then I just move a picture there. Okay, we're going to say we're going to do fisherman JPG, like our capture of the satellite. We have the two scripts, one for signing and one for verifying. And then what we're going to do is just check that our physical TPM, the TPM that we've been talking about, is working. So we just generate a random number. We say, okay, this is working. This is interacting with the board. And now we run these signature keys. As you remember, we check the TPM lockout counter if it's been used before in a non cool way. And then we have all the signatures, and all of these happen like pretty quick in an old, in a 10-year-old, Raspberry Pi. And then what we're going to do is just to check what is created, and then this directory was created with all the files inside. As you can see, you have the capture, you have the zip package to be sent, and all the things that we created, the signatures, the hash, and everything. And this is like a walkthrough through all the files for you to see that this happened really, and the content of the files. That's pretty quick. So everything was created, and then what I did is just to list all the files that were created. As already mentioned, we have the original image, we have the hash created with our SHA-3 256, the signature of the TPM, the public key of the TPM, the MLDSA signature, the public key, and also the package that is ready to be transferred. And then I have the verifying script. So what I did is just run it, and what does the script? It's just check if everything is working. This is ground station side or reception side, let's say that way. So what is going to verify if the hash is okay and the signatures are okay and everything is okay and nothing was changed in the middle. I mean, no change in the satellite, nor in the ground station, nor in all the transit. So what we see here is like everything passed, the hash match, the classical signature with the TPM is okay, and the post-quantum signature is okay. So everything is fine. And now what we are going to do is to try to do something to break this workflow. We're trying to do something to break this in order to see that this is working. So what I did is just, okay, let's beam Fisherman. That is the capture. I just add one character, save it, and then I rerun the script so we can check it. And then what is going to happen now is the hashes are not going to match because that's okay, the image change. But the signatures are going to be okay because what we are protecting is the hash that we have in that file, you know. So we are going to have this mismatch. That is okay because we are recalculating the hash now with that change. And then the signatures are going to pass because we are not protecting the image in this case. We are protecting the hash because for us, the most important thing is just to be sure that that hash is protected and nothing can change it. We protect the image too, but in this case, that was the idea. Now, what we are going to do is just to modify the file, which is imagehash.txt, which has the hash of the file of the image. And what happened when we change it is that we are going to have the hash mismatch because of the image that we changed at the first step. And also we are going to have a fail on the signature checking because we already changed the file that is protected. And maybe some of you ask why you are protecting the file with the hash and not the image. And the thing is, like, at the time I did the research, the TPM can handle so much bigger images. So what I needed to protect is like something pretty small that is the hash because I can sign it with a TPM. Now, for example, doing by software, it's possible to do it this way with more bigger files. So as conclusions of this post-quantum test or proof of concept, we can say that, okay, we can sign pretty confident and that it works using the TPM. Also, it's possible to do this hybrid signing using MLDSA. It works too. But it's something that is important to have in mind. At the time, because we don't have the TPMs that can handle quantum algorithms, we don't have this property of the TPM that protects the private key. So it's not hardware protected, not yet. So we need to think in using like an isolate domain. If, for example, we are going to use on FPGA or maybe using it by software, we need to just think in our threat model and how this could be exposed. Okay, again, we need to check how this evolved when TPMs that handle quantum just appear. And also, this is the final conclusions that we could have. This is working in pretty old hardware. Also, we can have the TPM with the DC identity bind to a satellite. And also, it's possible to start with this hybrid approach. And also, well, we need to see what happened with these new chips. So, as I already mentioned, first of all, thank you for being here, for listening to me. And everything is published in GitHub with all the code and everything. And there's a pretty cool blogspot post with all the information here. So thank you.
Thank you very much, Juani. Do we have any questions from the audience for Juani? Yes, please.
How long are your keys? 64, 32? How long are your keys?
Oh, pretty good task. I need to check because we did a lot of tests, and I'm not sure what we're using for the. You mentioned for the demo.
Yeah.
We can check.
Yeah. And the second question is: have you thought of a scenario attack with a sufficient quantum computer who could actually reproduce both your keys?
Well,
of course, they have to also match it, but with enough?
Okay, no, the thing is like, it's supposed that if you have these quantum resistant algorithms, it's supposed that everything will be okay. I mean, everything will be okay. It's supposed. But the thing is like, no, we really don't know that. And also because, as I already mentioned, we just starting testing this like 2 weeks ago, that we have this access to this solution that is by software. And also we have this issue of where we are going to store those keys. Because for sure, we are assuming that we have someone in the satellite or could have access, and for sure they can be stolen and they can be used. I mean, not even calculated, you know? So for us, the most important thing is the threat model and how you think the architecture or where you place those keys. Even when we don't have the TPM, that where we can just place them inside that hardware. But yeah, it's a really good question. Thank you.
Thank you. Do we have another question? Maybe a last one.
You have the public key in your signed package. How do you validate that the public key is indeed the public key of the satellite? Do you have a public key infrastructure around that? Or is it signed?
Sorry, can you repeat?
The public key, you have it in your signed package. So you only verify against this public key, but how do you prove that it's the public key from the TPM?
Because the thing is like, before, just integrate the satellite, you can generate the keys, and then you can store the public keys that you are going to use to check what is received by the satellite. So that's why you just get those public keys and store it in order to check. And also you can include them because it's okay to include the public keys. I mean, it's okay. You can just take them off.
Makes sense, thank you.
But it's just to verify.
Okay, so thank you very much again, Juani.